today actually we have been talking in this session a lot on energy savings, solar control glazing. And what I want to show you today is the work we do at TNO and the BRIGHTLANDS Materials Center on solution process thermochromic coatings for energy efficient glazing. And before we go into the subject matter, I want to just explain a couple of things on what BRIGHTLANDS Materials Center is. So TNO is an independent research organization in the Netherlands, and together with the province of Limburg, we work together in the BRIGHTLANDS Materials Center, which was founded in 2015 and is located very close to Maastricht at the Gemmelot campus in the south of the Netherlands. And our proposition is actually to work in application-driven research programs. So our focus is in new developments in polymeric materials and in coatings. And we work in 3 different programs, which I will introduce in the next slide. We are very application-driven. We always take care in the projects we do that we have a good representation of the value chain. So from a material supplier to the end user, typically. We fancy actually collaborating in shared research programs. We have a strong network of regional partners, but also national and international partners who participate in these programs. And actually, we combine we basically bridge the academic world with the industrial world. And what we do is actually the in-between research to pick up interesting academic concepts and try to bring them to a level where they are interesting enough for industry to pick them up. And these are the 3 research programs we are involved in at BRIGHTLANDS Materials Center. So today I will be talking about the Sustainable Buildings program and then focusing on the solar control glazing activities. Next to that we have a program on 3D printing where we focus on new polymeric materials and processes to make 3D implants as well as automotive spare parts. So it's 2 different lines here. And the lightweight automotive line focuses on reducing weight in automotive applications, so replacing steel with thermoplastic composites to reduce energy consumption and to reduce CO2 emissions in automotive applications. Now, what do we want to do in sustainable buildings? And I think many of you share that ambition. We want to develop innovative materials for use in building skins, which will decrease the energy consumption of a building. And with the energy consumption, we want to reduce the level of CO2 emissions. And I will talk about the potential we have there in a couple of minutes. But it also works with respect to level of comfort, natural lighting in a building, ventilation, and so on. And we focus primarily on the building envelope. And part of the work we do is focused on glass, and part of the work we do is focused on the non-transparent parts. And today I will be talking about the energy efficient glazing activities we have. So this actually we already saw this morning in the first presentation in this session by Glass for Europe, who presented this TNO study on the potential energy savings if we move over to highly energy efficient glazing systems in Europe. And what was surprising to us actually at TNO when we did this study, and which is still surprising to me, is that if you look at the average performance of the EU building stock, we are still left with a system with a U value, a thermal insulation properties of 3.4. So we have a lot to gain there if you look at energy efficient glazing, which is already available. And certainly if we proceed beyond that state of the art. And this details a little bit more what we can gain if you look at this over the entire European countries. So this is the annual energy saving we can reach in 2030 if we change the window stock actually in Europe to high performance glazing. So it's a dazzling large number actually which we can save, and it corresponds to 94.3 megatons of CO2 equivalents per year, which we can save if we move over actually to high performance glazing. And this would mean a reduction of 30% in the energy consumption of buildings. And that actually holds more or less for all the individual European countries. So if we look at the European countries, and I just picked some of these out of the list. By the way, the report, the underlying report is publicly available and you can easily find it on the internet. If we detail it out for a couple of different countries, we see that the potential for energy savings in Belgium is about 32%, Estonia a bit larger, Germany a little bit smaller actually, but all in all you see that in every country there is a lot to gain if we switch from the current glazing stock actually in buildings to energy savings glazing, to high performance glazing. Now, what can we do there? Actually, what we are doing is focusing on thermochromic coatings. And here I put the solar spectrum. You can see on the left side up to 400 nanometers roughly, you see the UV part of the spectrum. Then you see the visible part here between 400 and roughly 750 nanometers, and the infrared part of the spectrum. And what we aim to do actually is get as high as possible in transparency in the visible, and then get a switchable system selectively in the infrared part of the spectrum. So without changing the visible transmission, we want to create a thermochromic system which can switch between transmission of infrared radiation and blocking of infrared radiation. And of course, we are looking to optimize the balance between transmission in the visible and solar modulation behavior in the infrared part of the spectrum, as I will show you in the next slides. So shortly going into chromogenic materials. In our case, we use as an external stimulus the temperature. So this autonomously switches, the system we develop autonomously switches between transmission and blocking of infrared radiation at a specific switching temperature, which we can program, so we can optimize that for the application of choice. It can switch back and forward, of course. So if you go to high temperature, it starts blocking infrared radiation. If you go back to lower temperature, it starts transmitting infrared radiation again. We can actually do that in two different ways, and we have demonstrated that on lab scale in two different ways. We can do it in form of a coating, a single layer coating system, which we directly apply to glass. And the coating system in our case is solution processed. I will tell a little bit more about that later in the presentation. But we can also do that with laminates, with interlayers. We can actually we can make pigments with the same functionality as the coating. So the same thermochromic functionality we can include in a nanopigment. And we can disperse these nanopigments, for example, in PVB, and then use an interlayer between two glass sheets, which has a similar functionality to the coating we directly apply on glass. So here you see it back. So what we are thinking about is actually, if we look at the coating, we directly apply a single layer coating system directly to surface number 2. So the outer glass pane and then the inner position basically. And if we work with a laminate, we include nanopigments in PVB in a simple extrusion process and use that for lamination of glass sheets. And here you see a schematic representation again between, to illustrate the difference between winter and summer. So in winter you want to get all daylight in, all the visible light, but also the infrared radiation you want to get in. In summer you want to get the visible light in and keep the heat radiation outside. Now if you then look at the energy savings, and I'm going to limit myself here actually to presenting results which are publicly available from literature. It's a bit of an older study from 2010, where they looked at the energy savings potential when you start using thermochromic coatings with respect to benchmark products at that point in time. And here in the left diagram, you see the energy consumption improvement, so the savings basically. And here on this diagram, you see the modulation behavior of a thermochromic coating in the infrared part of the spectrum. So 65% means 65% reduction or increase in transmission of infrared radiation, up to 10%, and in this case, a non-switching system. This is a sputter silver-coated glass, which is used as a reference in this study. And this is blue body tinted glass. And you see here actually another parameter coming back, and that's the switching temperature. So the black lines here, these are switching. This is a coating which switches at 35 degrees. This switches at 30 degrees, at 25 degrees, and at 20 degrees. And you see that a lower switching temperature in this case, under these circumstances, is favorable. And you see an energy consumption improvement with respect to clear glazing, uncoated glass, which is dazzling, actually up to 45%. And you also see in this case, and it's calculated for Rome here, because it will of course depend on the geographical locations and weather condition, the actual improvement you get. But you do see a solid improvement here also if you compare it to benchmark products. And at the moment we are doing similar simulations for our own product, which we hope to present in a later stage. And on this side here, you can see a little bit what happens if you look at different geographical locations. So these are 4 thermochromic systems which have been developed by this research group and are well described in this article. So these are real systems. Then this is again the sputtered silver layer, and this is the blue tinted glass. And you see here a comparison for different geographical locations. So you see Cairo here, Palermo. You see a huge advantage if you go to Rome, Milan. And then if you move here to Helsinki, you see that the advantage becomes a little bit less pronounced. So it is dependent on the geographical location. But overall, I would say it's a very interesting technology when you compare it to conventional low-E coatings. And here you see a little bit more detailed what you can save actually in winter and in summer. And you see that the biggest advantage for these types of coatings is actually in summer if you can save energy consumption and if you can save costs, because you don't have to use an air conditioning system, or you have to use your air conditioning system less than in a conventional case. If you then look at the proprietary thermochromic coating which we have developed, then it's a single layer coating. It's a purely ceramic system. It's wet chemical, so it's solution processed. So we apply it from a solution, a dispersion basically, with active material dispersed in a combination of water and alcohol. It's reasonably color neutral. And the interesting part is it has no color change upon switching. And you can see that already here for this example. And so you can see here at low temperature, it actually transmits infrared radiation. At higher temperature, it starts blocking infrared radiation. And you can see that the change in the visible part of the spectrum is nearly nothing under these circumstances. And this is just one example of what we can do. I will show you that we can tune the optics for the application of choice. We can also tune the switching temperature. That's related to dopants we use in these coatings. And we can tune, as I already said, the visible transmission and the solar modulation. It's a very thin coating. So I think the thickest coating I will talk about here is 78 nanometers in thickness. It's applied normally to one side of the glass. At this moment, on lab scale, we are using dip coating to get samples up to 50 by 50 square centimeter in size. For the end of this year, and especially for next year, we plan to move over to a solution processed coating application technology, which allows single-site application at higher production speeds. And it comprises VO2 as a thermochromic material, but it's combined with other materials basically to balance the properties of these coatings. Now, what does tailoring the optics mean? Basically, we can play with the coating thickness, and depending on the coating thickness, we can go to either a lower transmission in the visible or a higher transmission in the visible. And you can see that it's a trade-off between transmission in the visible and solar modulation behavior. So you see here in the red curve, actually, this corresponds to a coating which is 78 nanometer thick. You can see actually that we come up to about 55% in maximum transmission. And then you see a solar modulation here if you go to 2 micron, between 30% and roughly 75%. And so we can tune this. And just to show you that we can tune the switching temperature, we use dopants for that, and that's the advantage actually if you go to a solution process system. You can use all kind of combinations of ingredients to make hybrid coatings. And here you can see that if you do nothing, the intrinsic switching temperature of VO2 is approximately 70 degrees. And you see here that if we start adding dopants, that we can easily bring the switching temperature down to the point where you actually need it for your application. So close to 25 degrees or maybe even 20 degrees, depending on the application of choice. Now, how does that now look like in practice? It's very straightforward, actually. You see that we use these kind of liquid coating formulations. At the moment, we make those at a scale up to 5 liters. This is a mixture of water and alcohol, basically, with the active coating material dispersed in it. Then at the moment, on lab scale, we use dip coating, up to 50 by 50 square centimeters, to apply these kind of coatings. Then we need a thermal curing step at elevated temperatures to get the right composition of the coating and the thermochromic properties. And then we end up with these kind of coated glass paints. Now, if you look at the stage of the development, so where are we at the moment? At the moment, we are still working on a laboratory scale. We can easily produce 10 by 10 square centimeter samples using dip coating. We have, beginning of the year, acquired a larger dip coater, which allows us to go to 50 by 50, which we are doing at the moment. And by the end of the year or next year, we plan to go to 1 meter in size. We are still further optimizing our single layer coatings and scaling them up to pilot scale. We will proceed towards larger pilots in 2020, 2021. And we have selected roller coating there, actually, as the application of choice. And if you want to do these kind of sizes, it means that for the chemistry, we need to go to roughly 50 liters of formulation, which we can easily produce in our infrastructure. And we will also look at the potential of multi-layer systems, where we use this layer as a thermochromic layer in an interference filter to see what we can still do on the optics to get an even better balance between the solar modulation in the infrared and the transparency in the visible. And the second topic I want to shortly touch upon are the thermochromic films for lamination. I already explained to you that we can basically achieve a similar functionality as the one we have in coatings in, for example, PVB. And we do that by making pigments, ceramic pigments, which have more or less the same composition as the coating material we are using. And you can see here that it's based on monoclinic VO2. Also here, these pigments need to be doped. The key trick is actually to make them small enough to avoid scattering of visible light in these films. And so the pigments need to be smaller than, let's say, 70, 80 nanometers in size. If they are larger in size, then based on the refractive index contrast, you get scattering of visible light, which is undesired. So we can make them small, and we can make them switch, and we can make them switch over a number of cycles. And here you see a calorimeter. This is an XRD showing that we can actually make phase pure VO2. And this shows you actually, and this is an undoped version, so the switching temperature is at 68 degrees. This shows in a calorimetry experiment that the pigments we are actually producing, that they nicely switch. Based on the surface area here underneath this curve, we can also determine the purity of the material. And here you can see that it also switches back if you start cooling the sample. And you can do that in numerous cycles. And we brought it up to 100 cycles up to now. And we are testing basically what the limits of the system are. Then if we have these pigments, we need to introduce them into polymer films. And what we normally do is first do the synthesis. Then we do a surface functionalize. We need to surface functionalize these pigment particles. To tune the interfacial tension to get them into PVB. And 2, also to give them a kind of a protecting layer to stabilize them in these polymer materials. Then we have a master batch as a result. And then this master batch is actually used for extrusion of polymer films. And here you don't see an example with VO2, but here you see an example with titanium dioxide. And with titanium dioxide, you of course see that if it's a larger particle, that you start getting scattering in your film. But we made similar films with PVB and VO2 as the active pigment ingredient. Now, what do we do more than this? I've been talking mainly about this and about films. We're also working on films for lamination of solar panels, and including optical pigments there to improve either the performance or the aesthetics of these kind of panels. And we're also working on BIPV, on coatings basically to get color onto BIPV panels without hugely interfering with the panel efficiency. Of course, if you bring color actually on a panel, you always lose some efficiency because you lose light. But here we play with reflection rather than with absorption, and we can make a system which is tailored for a very narrow band, which minimizes the light losses and gets a very interesting color to these kind of PV cover glasses. Then in all projects, we do actually in all 3 of the programs, but certainly also in sustainable buildings. We work together with partners both from academia as well as from industry, and also with other knowledge organizations. You see here, for example, that we also work together with Fraunhofer ESC on these kind of topics. And before finishing, I want to thank a few people. First of all, my team, which comprises both permanent staff from TNO as well as students, the partners who are involved in the projects, the funding agencies, the province and TNO. And I want to thank you for your attention so late on a Friday afternoon. Thank you.
Thank you very much, Pascal. Do we have any questions for Pascal on his presentation?
Hello.
Hi.
When you dope your material to lower the transition temperature, do
Yeah.
you see an effect on the transmission delta that you can achieve?
That very much depends on the type of dopant you use. So if you use a conventional dopant, which is well known actually for VO2 system, then people use tungsten. If you start using tungsten, then you lose the switching or part of the switching performance. Basically, part of the proprietary system is here that we develop dopants which minimize that loss, basically. So you lose a little bit compared to the undoped material, but it's really minimum in our case.
Thank you.
Any other questions?
Yeah, involves obviously really some cool chemistry. Can you comment on the speed that you envision for the roller coater for the later on?
Yeah, so we are aiming there for a speed of about 5 meters per minute. I think that's a realistic speed to aim at, because we know that roller coating is, for example, also used to apply quarter wave anti-reflective coatings. And then you're talking about also sol gel systems, similar coating thickness. And there we know that 5 meters per minute is roughly the speed you can achieve with this level of accuracy. So we are aiming for similar results actually with our coating system.
Any other questions?
To my knowledge, one of the difficulties of the thermochromic is their brownish aspect. When you dope, do you improve or degrade this slightly colored aspect of the thermochromic?
Actually, when we dope with the dopants we selected, we don't see a huge effect on the color, basically. But we did manage to get it more. Conventionally, one of the problems with VO2 is indeed the yellowish color, actually. That has something to do with the purity of the material you're producing. So if your material is impure, then you get more yellowish colors. If you have V2O5, for example, as an impurity, that negatively affects the color. That's one thing, basically. And the second thing is also the coating composition. So if we don't use a pure VO2 coating, we use a coating with other types of ingredients, basically, which gives us a better balance between optics and the desired performance of the thermochromic coating.
Thank you.
We probably have time for one more question if there is one. Yes.
I was looking at your DSC results, and I could see like different peaks in heating and cooling.
Yes.
So it must be like any stasis between heating and cooling cycles.
Yeah.
Do you think that's there's any positive or detrimental effect to the building performance of thermochromic?
For the building performance, you need to keep the hysteresis as small as possible. If your hysteresis broadens, actually, that has a negative effect on the energy gain, on the energy savings for these type of coatings. But there is always an intrinsic hysteresis if you use these kind of systems, and we managed to minimize it for the coatings to approximately 7 degrees. Temperature difference between switching from low to high and switching the other way, basically. And that's the same which we managed to do in pigments. And that's more or less the minimum I think you can achieve for these kind of systems.
All right, ladies and gentlemen, let's give Pascal a round of applause. Thank you for his
Thank you.
Hi there. Did you like what you just saw? If you did, why don't you like the video, drop us a comment below, and share the video as well, since GPD is all about sharing. And to receive more videos in future, subscribe to this channel and don't forget to click the bell icon. Ciao!